And now you can hear me. Okay. I was doing a nice digression on the stuff. It appears that the Microsoft was suffering, and so thanks, Barbara, to let me know. Okay, people didn't hear my digression on YouTube. The long story short, I mean, for those that are start following now, you didn't lose much because I was just doing a recap of the previous lessons. And what I have introduced so far, and now I have 0 concurrent viewers, which is a drama. No? No, I have 1 concurrent viewer. Barbara, can you tell me whether you hear on YouTube? Write on Telegram, please. Okay, I will edit the lesson. So, welcome to this new episode of Probabilistic Robotics. So far, I did a wrap up and mentioning what was happening in the... But it's weird. No. But how comes that the microphone is not functioning? Properties? Jabra. Okay. Si sente o non si sente, ba? Si sente? Ah. Because Comic. How to do properties. Jabra. Okay. Close. Jabra always worked. Microfono si sente o no, Barbara? Ok. Ok. Perfetto. Okay, guys. I think it's also even too loud. Probably. Is the audio quality fine? È la qualità dell'audio sufficiente? Sì? Okay, excellent. So now, I was doing, sorry, I mean, now I am on tethering with a mobile phone, so that at least we do not have network issues. Like for the people in the class, I apologize because of the streaming issues. What I was doing a recap on the course. Nothing spectacular. Okay, a little bit louder, they say. A little bit louder. A little bit louder. Now, a little bit louder. Can you hear me? Can you hear me? So now I have to wait 6 seconds to figure out whether, because of the lag. Meglio? Anyway. Excellent. All right. So we have around about 20 seconds of delay between things, between a bounce of the message. So it's like on the moon. What I would like you to think about what we have done so far in probabilistic robotics is that we presented you techniques and we presented you problems. And we have presented you 2 important problems in robotics, which are localization and SLAM. with and without data association, as exercises, as problems, right? And then we had in our pot the filter, and we used the filter to solve these problems because that's all we had so far. But you could solve them in many different ways. And also, it's another important aspect. In this discipline, and in robotics in general, you have to build a system. The problem never comes to you cooked already with the landmarks organized in a vector ready for you. Hello, hello, I am a landmark. No, that's not the way it comes. You have to operate on real data, and typically you have to manipulate such a real data in order to implement the solution that you have in mind. And often you have to, the system is not restricted to the application of one single technique. Oh, here I use a filter, and then problem solved. That's not the way. You often have to implement additional mechanics for creating the landmarks upon need, in case of SLAM, or whatever, for initializing the system image, right? Because you might also want to have the filtering works as long as the state estimation is more or less fine, especially Kalman, because you have a Gaussian distribution. But if you don't know where your robot starts, imagine a localization problem where you start your system from scratch, right? You don't know absolutely where it is. Then you could model it with a unique large Gaussian, which covers the entire environment. Then the robot sees a door, and ideally the real posterior, real distribution that you would see is that you would have a little high peak of this distribution in front of every door, because if the robot sees a door, it means that he's in front of a door, right? But this is not a Gaussian distribution. So this would not work with a traditional Kalman filter because it expects a distribution like that. Instead, your filter will estimate a unique large Gaussian, which is more or less compliant with the observation, but it doesn't manage to do so. Okay, guys? And this is typically the case when you don't know data association, because if you know data association, at least you know which door you are in front, and then you can do something. Okay? But not always you know data association. What you might expect at the exam, and there are texts of the exam, and there is a very valuable piece of information that I've given you about filters in the text. There was this PDF that I've given you, how to approach filtering problems, right? But in general, remind that during your working life, you will have problems which do not come cooked as we cook them for you. You will have to invent and implement all the glue around. Okay? So now, speaking about what we have done so far, we started from probability. Sorry, I have to put the glue. Sorry for those in class. We started from manipulating density distributions and then learning how to manipulate densities. Then we approached the filtering problem, which is estimate the current state given the previous states and the previous observations. And then we implemented the first histogram filter with the grid ratio. Then we restricted ourselves to the Gaussian distribution, and we have found that the Gaussian distribution is spectacular because it's a continuous distribution that remains closed under certain assumptions. Then leveraging on these assumptions and then restricting ourselves to linear systems, then we were able to devise the rules for the Kalman filter. And then so far we approached the first problem, which was localization, the very first filtering problem that we have approached. And then we approached SLAM, another simplistic filtering problem that can be derived by localization just by seeing new quantities in the state. Because that was it. But clearly these new quantities concur in the definition of the observations. Right? But then they are more or less not the same, because one is more complicated, more complex. You have a larger matrix in SLAM than in localization, but conceptually they look alike. Right? Like one is a subset of the other. Okay? And then we did all these fantastic things with the Gaussian assumption. We have found that the Gaussian distribution has nice properties, and we were hammering the Gaussian distribution through nonlinear functions just by closing our eyes and saying, you know what, this function might not be that linear, but I treat it as if it was a linear function because we use the Taylor expansion to approximate this function locally. Okay? And that is basically the mechanism behind the EKF. Question is like, how approximate is this operation? If though, on the one hand, we know that the Gaussian that goes through a linear transformation remains a Gaussian, so we don't do any approximation error in doing this operation. If we have a nonlinear function and we linearize the function and then we pass a Gaussian through it and then we get another Gaussian, we will have some approximation error that comes from the fact that this object here was a curve. I treated it as if it was a line, and then once projecting the Gaussian through it, I should get some mirroring effect. The shape that I have through this projection operation shouldn't be a Gaussian anymore because I have distortion. Okay, that's the case. And then by feeling, I can tell you that the quality of the approximation is the worse, the more large is the Gaussian in input, right? If I have a very large uncertainty in my x variable, and then I project this uncertainty to a nonlinear function f of x, means that in order to have a reasonable approximation, I will have to consider many values on this large input Gaussian, right? That would then cover a big region of my function, which then is poorly approximated by the plane. So if I have a large covariance matrix, crudely speaking, and I pass it through a nonlinear function, then the resulting Gaussian approximation is poor. Okay? Because this means that I would have to consider a big region of the plane under which I perform the projection, and this big region of the plane is going to be deflecting, is going to be a poor approximation of the function, of the nonlinear function that it's intended to approximate through the Taylor expansion. Just to make you an example, I put myself big. No. You do this. All right. Visible, more or less. And the chalks are present. Yes. If I have, this is a generic nonlinear function. Sorry, I have to draw here because this is a generic nonlinear function, right? And this is my Gaussian distribution. This is my f of x, right? And if I have a Gaussian distribution which is like that, or which is very big, so this is my Gaussian distribution on the x, right? Then what I would have is that I would have to compute a Taylor expansion around this region. Then I would have, this would be the plane. Then I would project the Gaussian through this, let's say this way, position, and I would have another Gaussian here, right? Now, if this Gaussian is very wide, right, I take this Taylor expansion over here, which is maybe something like that. But then it's a much poorer approximation because I would have all sorts of distortion and all sorts of bumps once I project the points through this nonlinear function. Okay? So the closer is the error, the covariance, the better this approximation will be. Just by giving you an intuition on when this Gaussian approximation works. Now I become smaller, and I sit again. All right. Clear? Now, the question is like, can we do something better while propagating the Gaussian distribution through nonlinear functions? That's the question that we have. We like pretty much Gaussians because they are closed. Let's say I want to restrict myself to Gaussians, but I'd like to have a better approximation than the one which is obtained by straightforwardly passing through a plane. Ideally, I would like to take each point here, project it through the function of the distribution, then I get a sample distribution, and from this sample distribution I could reconstruct the parameters of a Gaussian through the covariance matrix and the mean. Okay, guys? That would be a brute force approach. Like, did you understand what I'm saying or not?
No.
Excellent, thank you. Like, let's say that I have a situation like that. Instead of doing a planar approximation, this was my nonlinear function, ugly as it is, and I have a Gaussian distribution as input, right? And I'd like to recover a Gaussian approximation of f of y. Okay, guys? Oh, I have to become big.
So the product of the Gaussian,
The
product of the Gaussian, is it the product of the Gaussian and the new function?
The problem is that I want to have a Gaussian as output, right? Doing a planar approximation, I could get a Gaussian, but I would have a Gaussian which is resulting only from projecting this to through the tangent plane of the mean of this function. Okay? Understood?
Which operation are we doing with the function of the Gaussian?
Fy is equal to f of x. We want to find the normal approximation of the random variable y. Okay? Now, if f of x would be ax, then we know that the covariance matrix will be A sigma x A transpose. If f of x would be approximated by a nonlinear function, we would know that the mean is just f of mean, and the covariance matrix is J, where J is the Jacobian of f of x evaluated in the mean, would be J sigma x J transpose.
No, sorry. If you don't understand the operation, so we have a function.
A function f of x.
Okay.
X is a random variable, normally distributed. Y is a random variable by itself, right? Okay, now if f of x would be a linear function like ax, y would be normally distributed. This is the core of the Kalman filter, right? The core of the Gaussian manipulation. Look back in the Gaussian manipulation. Okay? If f of x is not linear, so it's not in the form ax plus b, but it's in another form, what you typically do is that you approximate this f as f of x0 plus j of j delta x, where j is the first derivative of x calculated in or the first derivative of f calculated in x0. Normally, what you typically do is that you obtain it, like you boil it into an affine form, where this becomes the A matrix, and where this object over here becomes the A matrix. Yeah, they don't see it all. But did you watch carefully the Gaussian manipulation?
Yes. So we have x as the Gaussian.
If you have a function f of x, you do the Taylor expansion. Now you say that f of x is more or less equal to f of x0 plus df over dx, which is the j, no? Df over dx times delta x, right? Okay, this is a constant C. This is a matrix A. No? You boil it down to an affine form. Agreed? Okay, and therefore, that's the mechanism that you typically use in the Kalman filter to propagate a function. You boil it down to an affine form. Once you have a Gaussian that passes through an affine form, you have the closed parameters of the Gaussian.
Okay.
Is that clear? Right. Now, the problem is like, if this act, like you can picture this process just by saying, okay, this is the Jacobian, right? It's the derivative. We basically project this through this. So you project these two values over here. You project them here, and then you get let's say the flex point of the new Gaussian. Okay? Agreed? Very good. Now the problem is like if this Gaussian distribution has the same mean but is much broader, like that, right? What would happen is that, well, it's much wider, right? This is the mean, right? Let's say I project this point through here, and then I get this value. And then I project this point here to here, and I get this value. So I will get a very large Gaussian as output. Do you understand? Is it correct? But I don't think so, because here the overall slope of this function should be this, not this. Right? Okay, this is the message. So, linearizing a function in order to calculate the Gaussian assumption might not be a good idea when you have a lot of uncertainty in the input distribution. Because during the projection operation, you are going to stimulate areas of your Taylor expansion which are poor approximation of the input function. Agreed? Do you see it now, guys? All of you? Very good. Now, my question is like, how can I mimic? I still want to have a Gaussian approximation of my output distribution. I still want to have a Gaussian approximation of f of x, of y equals to f of x. So I still want to have a Gaussian approximation. I know it's not a Gaussian, but I want to have it as a Gaussian because maybe it's convenient for me, right? What could you do? Classical way, like a brute force approach, a computer scientist approach, would be, I take, this is my Gaussian distribution, I take a set of samples through this distribution, each sample with its own weight, let's say this way, and then I take this sample and I project it here, and I have this sample. Take this sample and I project it here, and I have this other sample, I take this sample here, and I project it here, and so on. So you project all the samples through the function, right? Understood? Clearly, in the middle, you will take more samples than on the corners, just to mimic that you have a higher probability mass over there. And then, in the end, what do you do with this set of samples? Through a set of samples, you can reconstruct the mean and you can reconstruct the covariance. Right? You can reconstruct the mean, because that's the mean, and you can reconstruct the covariance, because it's sigma, so that's a formula to calculate the covariance, given in the lesson on the Gaussian distribution. Right? And then you would have a better approximation in theory of this Gaussian distribution in the output. It's not a Gaussian distribution what you will get, in fact. But you say, okay, you know what? I recalculate the parameters of this virtual Gaussian. Is that clear? Very good. Now, and this brings me to the Unscented Transform, which is a new way to represent the Gaussian in a way that this operation leads to a better approximation. Okay? Now it becomes small again. The audio is good. Tell me, folks, if the audio is good. I have only one person watching. And that's the game. Now, let me become a little bit smaller. It's fantastic to be able to see myself on the screen, like to see what you're seeing. All right. Now, we all know, right, that the Gaussian distribution has this form. Do you agree with me, guys? If you need some time, and if you have some questions, please, my 5 students, raise it, shoot a Bengala, do anything that... All right. Agree? It's nothing, it's now no shocking, no? You see it and you should rejoin, because now we will ping with this Gaussian distribution as we want. Oh, sorry. Problem with 2 screens. Okay. Now, another way through representing a Gaussian, which is in the end a shape, right? It's an ellipse, if you want, or an hyperellipsoid. How would you represent an hyperellipsoid in space? One idea, an ellipse in a space. There are many parameterizations. You could represent an ellipse, for instance, through its center, right? And let's say through the length, an angle, right? The orientation of the ellipse, and then the length of the axis of the ellipse. This would be a way. Or, if you're familiar with these vector graphics programs, have you ever done the splines, the curves, these curves that you can then stretch, and then you have control points that allow you to, you have a circle and then, or a curve, and then you pull it from a certain direction by putting a control point, and pulling this control point there, and then you see the curve bending. Have you ever done any editing with these vector graphics programs like Inkscape or so on? No? Inkscape. This requires Inkscape. Da, da, da. No. How to do a curve? There must be a way of drawing a curve. This. Okay. Have you ever done something like that? You see that I have control points. The more I pull them, the more I stretch the shape. Okay? This is an example. It's like, what is this control point doing? Well, this control point is basically controlling at this intersection of the curve the derivative of the function in that point. And the more I pull it, the more I say I want you to be stretched in this direction. Okay? You never played with these programs. Funny. It's funny. Okay, now I might spend hours in doing curves, and I stop. But this is the concept of control points, right? By pulling or by moving the control points, by moving the control points, I might, no. Control Z. Now there should be a way of dragging the things. Now I don't have it because I'm not familiar with Inkscape, that familiar with Inkscape. But I think if you do this, here you see, if I do this, I change the shape, right? If I do this, I change the direction. Okay? Right? So this entire curve, all this curve is parameterized by this point, 1, 2. For each point you have 2 points, one on the left and one on the right, that denote the stretch. Okay, guys? What I want to give you is a visual feeling of what it is. So all this curve, all of it, is summarized by the points that you see marked on the screen. Okay? Clear? Now, following this idea, if you have an ellipse, wouldn't it make sense to represent it as a set of control points? Maybe redundant. Maybe they are more than needed. Okay? But you might have a control point in the mean that moves the ellipse. Then you might have 2 control points on the 2 axes and 2 other control points on the other axis. If you pull them, then you make the ellipse fatter in one direction. If you pull it in the other way, you make the ellipse fatter in the other direction. If you rotate it, then you rotate the whole ellipse. Agreed? You feel it? Very good. Closed Inkscape. No. Okay. All right. Now, what if we represent the Gaussian as a set of control points? No? Like, let's imagine that we put, just for imagination, we put the control points in a very intuitive way. We put 1 in the mean, and then we put 2 along the dominant axis, plus minus, and 2 along the non-dominant axis of the ellipse, right? Now clearly, pulling these 2 further will stretch the ellipse in that direction. Making them closer will make it more compact in that direction. Shifting the mean together with the other control points, they are redundant, guys. They are redundant. But still, it's a way to represent it. Okay? Understood? In this way, if I...
When you cut the Gaussian with a plane at different heights, we get different ellipses. Right? So
I said that they are not unique.
Yes,
I'm giving you the intuition, then we go to the algebra. Okay, let's say for now that we cut them at the height of the flexus, which is 1. Okay? But that's not exactly the case. And it's also not the way the Unscented Transform puts the points. Okay? Because it doesn't put it along the eigenvectors of the ellipse. It puts it somewhere else. Because calculating the eigenvectors, especially for high-dimensional spaces, is not something you want to do. Okay. Now, but you can imagine that we can represent our Gaussian, instead of with a mean and a covariance matrix, we could represent it by a set of control points. How many control points? 1 for the mean, and 2 for each dimension of my space. So a two-dimensional Gaussian will require 3 control points. So 3 numbers. 1 is the mean, and 2 are the left and the right points. Okay, guys? I have one more in the two-dimensional case, in the one-dimensional case, because in the one-dimensional case, I have one value for the mean and one value for the covariance, which is symmetric. Right? In the two-dimensional case, I have 2 values for the mean, and how many values for the covariance? Lower triangular matrix. I have xx, yy, and xy. Yx is equal to xy. So I have 5 parameters. Okay? In how many numbers would I have in a two-dimensional Gaussian to represent a two-dimensional Gaussian with this representation? Well, how many control points do I have? 5. 1 for the mean and 2 for each axis. 5, right? And how many numbers do I have? 5 times 2, because every one is a vector, is a 2D vector. So I have 10 numbers. 10 numbers versus 5 numbers. I have more numbers. Okay? Clearly, I have more numbers. This means that the sigma points will not be unique, because to the same Gaussian, multiple ways of the sigma points might represent these control points. In addition to that, to each point, you attach also one thing, which is so-called a weight, no? How much this point matters, right? In the end, in order to reconstruct a covariance matrix, you have to sum to reconstruct the Gaussian, you have to calculate the mean by summing up all the samples and extracting the mean, and you can calculate the covariance by doing the same outer product between the difference between the point and the sum of the outer products of the difference between each sample and the mean. Sigma is equal to the sum over I of x minus mu transpose, where x is the sample. Look in the Gaussian manipulation formulas, right? All right, I have one more degree of freedom that I call it a control point. What do you do with the weights? Well, simply the weights, you use them to score the points. So instead of being just a plain sum, it's a sum where each addend is scaled by its own weight. Okay? The heavier the weight, the more that point will mean. All right. Now, let's now introduce two. So we said we have a change in representation. On the one hand, we have the so-called moment parameterization or the canonical parameterization of the Gaussian. And on the other hand, we have these phantomatic sigma points, which are the samples. Right? We would like to now write two functions. One function that, if I give you a mean and a covariance matrix, returns me the set of sigma points, and also the opposite function, the function that, given a set of sigma points, returns me the parameters mu and sigma. Okay? If I have done that, I'm able to switch between the two representations as I want. Agreed, guys? Clear. Let's move forward. Now, that's the definition of sigma points. Why I repeat once again, it's not a unique way to extract sigma points, because I have much more parameters than the minimal parameters of a Gaussian, which means that there will be multiple combinations of sigma points that represent the same Gaussian. Okay, guys? But through some parameters, you can select something which is reasonably unique. Each sigma, how many sigma points do I have? If I have dimension n, I have 1 for the mean and 2 for each dimension. So I have 2n plus 1 sigma points. Each point, sigma point, is characterized by a position, position in the space, and two weights. One weight which is used to calculate the mean, and one weight which is used to calculate the covariance. Why that? Because the mathematicians wanted so. Okay? Two different ways. Okay?
The sigma points are the control points, right?
The control points, exactly, with the weight to which we attach the weight. Like now, I started talking about sigma points. See, the sigma points are the control points of my figure. Okay? To which I also add additional information, which is these two weights. One weight for the mean and one weight for the covariance.
Is there a conceptual reason why we have different weights for the mean and covariance?
Yes, because it's still an approximation, and according to the parameters of your, normally you do it to fit something into a Gaussian, right? What you will have is not really a Gaussian, it's something that is Gaussian-like, right? By having these 2 degrees of freedom, you can tune the behavior of the thing by spreading, let's imagine you have the weights for the covariance, right? Then you have these points, like which are on the axis, just to imagine, no? You have 2 points on the axis, one here, and 1 point for the mean, right? Then you are going to calculate the covariance matrix. If you could obtain the very shape of a Gaussian if you have the mean that has a very high weight and these points that have a very high weight too, because then you will get this shape. But if you and then you have these 2 points here, regardless how far you pick them up, because the weight has also an effect on the shape of the Gaussian. Because if you have a mean which has a lot of value, right, and then you have 2 points on the side that have a small value, what would it mean, this? This would mean that you would have a Gaussian which is like that, right? But you could also pick up 2 points which have much higher value, but which are much closer to the mean, right? And then you would get the same Gaussian, so to say. Understood? The point on how to choose, so you have this additional degree of freedom that allows you to position the points in the space while preserving the same distribution of a Gaussian. Now, by having this knob at hand, this possibility of changing of these over parameters, so these additional parameters, you have to think what happens when you project a Gaussian which is distributed this way through a function. If you have a very dense representation, then basically you would project them, you will get a very dense representation in out. If you have a sparse representation, then you will capture more of the morphing function that is used to project the points. Okay? So this is the reason. But normally, this is what I'm teaching you. This is the way the sigma points are constructed. There is a control points, and there are 2 weights, one which is used for the mean and one which is used for the covariance. Understood?
So you are saying that we have infinite possibilities or represent the Z Gaussian by changing the value and the position of the covariance?
The weight of the sigma points, and by changing, let's say this way, for a Gaussian, the minimal number of parameters, say for a 2-dimensional Gaussian is 5, right? 2 for the mean and 3 for the covariance matrix. With the sigma points, you represent, how many numbers do you have for representing this function, this Gaussian? You have 10 numbers that are denoting the sigma points. So you already have R5 degrees of freedom. But then for each of these points, you have 2 additional degrees of freedom. One which is the weight for the mean, and the other one is the weight for the covariance, right? So you have 12 degrees of freedom versus 5, right? With these 7 more degrees of freedom, you can play much more, still representing the very same function, once converted to a Gaussian. Okay? That's the meaning and how to choose it. Normally, what I do, there are some constants that allow you to select the weights. Once you determine the weights, then also the position of the sigma points is somehow established up to a certain point. And then you work with it. And there is some golden rule on how to select. But now we don't go faster. Let me reach the point. What was important for me now is that you understood that I go from a minimal parameterization to a parameterization that has a little bit more numbers, right? And with these numbers I can play. And also you understand the meaning of these numbers. These are control points that are put in the space that if I stretch them, that means that I make my distribution broader. Okay? Clear? Very good. Now, each of these samples is characterized by a position, by a weight that I use to calculate the mean, and by a weight that I use to calculate the covariance. Now, the first question that I might ask is that, okay, now, if I give you a set of sigma points, would you be able to recover the mean and the covariance? Straightforwardly, yes, because the mean would be nothing else than the sum, the weighted sum of all the points. Each sample is weighted by the mean weight. With this I on top in brackets, we denote the number of the sample. No? So I will go between 1 and 2n plus 1. Okay, guys? Do we have doubts on it? No? Very clear. For the covariance, well, we unroll the equation of the covariance matrix, right? Only that we scale this is the difference between the sample and the mean, no, in outer product. So vector times vector, that gives me a matrix. The sum of little matrices where every matrix basically adds a contribution to the covariance matrix, which is proportional to the difference between the point, the sample, and the mean, right? And each of them is scaled by the corresponding weight. Understood? Okay. This was almost obvious, I think. Clear? Now, why do you talk about Cholesky decomposition, Giorgio? Because this is something that you might want to know for when you grow up. The Cholesky decomposition is another decomposition of symmetric positive definite matrices. Basically, if you have a square symmetric positive definite matrix A, you can calculate through its Cholesky decomposition, which is a unique decomposition, the so-called square root of the matrix A, which is a lower triangular matrix that multiplied by its transpose returns the matrix A. Okay? It's often referred to as the square root for a matrix. Okay, guys? It's a decomposition. How to calculate the Cholesky decomposition? It's a variant of the Gaussian elimination algorithm. Okay? It's a variant of it. When you triangularize a system, right? Have you ever triangularized a system in your life? Calculated the triangularization of a matrix? Even by hand? Never? Never.
It's the standard Gaussian elimination, right?
Yeah. It's a variant of Gaussian elimination. No, you calculate it triangular. You can use it also to calculate the inverse if you do it on the bottom, on the right and on the left in order to get the identity, and then on the symmetry you have a specular matrix to get. That's how you calculate the inverse, by the way. You never ever do the determinant with the cofactor expansions. The determinant of no, that's not the way. You triangularize a matrix and then you calculate the determinants on there. I mean, these are all obscure things because you think that MATLAB is intelligent, right, and does the things for you. I recommend you to get a book, Numerical Receipts in C, that you can have a look how this black magic works. That I think is foundational for an engineer. But it's beyond probabilistic robotics, just like giving you this insight. Because, doing the things by yourself allows you to understand what happens inside the machine. Anyway, the Cholesky decomposition, if you want, I can show you the algorithm of the Cholesky decomposition one day, but today let's focus on. Let's assume that there is a decomposition that in MATLAB is referred to as Chol. I will show you now. Chol. What is it? Okay. Chol. Octave. Click. I have octave. Now I am showing you Cholesky. Let's generate, I need a large triangular matrix, right? So rand rand 300. Okay, very good. Times J transpose. Okay, this is a positive definite symmetric matrix, right? If I do Chol of A, I get, in this case, octave returns me the upper triangular matrix, right? But if I do L or U equals of A, I'm just storing U times U transposed times U transposed E. No, what was U transpose times U? Sorry. Oh. Was A? U transpose times U, because U is the upper. U transpose times U. This was L. This is the result of the Cholesky of L times U is the upper. L U, right? It's like normally L is the lower triangular. Octave returns with the upper triangular. So the two matrices is one the transposed of the other. So I can get L is equal to U transposed. If I do L times L transpose, L times L times L transposed, I get, if I do A, so this is my original matrix, and this is the matrix obtained by multiplying the Cholesky decomposition by itself. Clear? Okay, that is the Cholesky decomposition. The algorithm is also quite simple. Takes polynomial time, so it takes a time which is proportional to the number of entries of the matrix times so 2n to the power 3. Okay? Understood, guys? Very good. Now, this is still much cheaper to calculate. And why is it called the square root of a matrix? Well, look at it. If I take the matrix and I multiply it by transpose, then I get the original one. This means that normally you refer to L as the square root of A, because if you take L and you multiply it by itself, transpose, then you get A. Okay? This is the Cholesky decomposition. Now, I told you it would make sense to extract the control points of my Gaussian distribution along the axis. It would make sense. The problem is that determining the direction of the axis would require me to calculate the eigenvalue decomposition of the system, which is very expensive. Okay? Because it requires basically solving a polynomial system of solving a polynomial that has the degree of the matrix. Okay? So if you have a system which is 1000 by 1000, then you need to solve a polynomial equation of degree 1000. Do you want to do it? No. The computer is slow? Yes. So you don't do it. Okay? You can do it, but you don't want to do it. So, is there any other thing that we could do? Well, think about the two-dimensional case. Do you know what is the flexus point of the Gaussian? So you know that the Gaussian has a certain point where basically its second derivative changes sign. That's a flexus point, right? The flexus point is the square root of sigma squared. So it's the points where the Gaussian, like the flexus, come on, you know from analysis 1 the flexus point. We're doing it at Elysium or whatever, that's the flexus. And the position of this point is sigma, the square root of sigma. So sigma square is the covariance. Sigma is the position of the flexus, the difference between the mean and the flexus. Okay? Understood? That makes sense to consider this as the control point, because it's some meaningful point on my unidimensional Gaussian. It's a point which is precisely identified from when my second derivative changes sign. Okay? And that's more or less the idea behind it. Now, clearly we have a set of vectors, like traditionally, like one way of extract these sigma points, first of all, we have to pick up a direction, right, for the sigma points, a direction. Now, if we have our matrix A, we calculate its Cholesky decomposition, which would look like a lower triangular matrix like that, right? Now, our matrix A is characterized by column vectors. So with this notation, A in bracket of I, we denote the ith column vector. Okay, guys? With the same notation, by brackets with I, we denote the ith column vector of the square root of A, which is take A, calculate the Cholesky decomposition, and then calculate, consider the first vector, the second vector, the third vector, and so on. Okay, guys? Is that clear what this notation means? Take A, calculate the Cholesky decomposition, and extract the ith column. Exercise, implement the Cholesky decomposition in C++. No libraries allowed if you want. No, if you want to do something, it's very simple. Like, really. It's a 3 for loops nested. Now, why did you talk us about the unscented, the Cholesky decomposition? Because I need it in 1 second. Now, we clearly have already touched in this lesson the argument that once I convert my minimal set of parameters to the sigma points, I have a bloating of parameters. So I have much more numbers than what I need to minimally represent the same quantity, right? And in particular, I have the sigma points, like this, the position of the sigma points, and I have also the weights, right? Then some mathematicians, don't ask me why, came out with a strategy to select a combination of weights and sigma points that is meaningful. Okay? That is meaningful, that has something like, while, so we want 2 quantities. We want that once we go to sigma points to Gaussian, to mean and covariance, we need to have the same distribution. But also we want that when we go from covariance to sigma points, now we're doing the opposite thing. Then in this case we have many degrees of freedom on how to choose the sigma points, right? While going from this direction is unique, because you have many constellations that lead to the same thing, while going to the other direction, you have certain, random things. So let me introduce these fantastic numbers, this kappa, this alpha, and this beta, that can be chosen, like later on you will see what are the numbers that you can use, that can be chosen basically alpha between 0 and 1, k should be greater than 0, and beta should be equal to 2. Ignore that, use these parameters, right? Use those, because those work. I tested them, I have been twiddling for a lot of time. They work. They produce a distribution of sigma points that makes more or less sense for the distributions that we have in place, like that we want to deal with. But imagine that to control the extraction of the sigma points, we have to select these 3 parameters, right? So I give you these 3 parameters, impose it, and once you impose these 3 parameters, then there is and once you impose the directions, we'll see how, then there is a unique combination of the weights of the covariance and of the mean that allows you to reconstruct the very same Gaussian. Okay?
If we start from a Gaussian that has one mean and for
one mean, of course, it always has one mean.
Of course. And 4 parameters, like 2 by 2 matrix, yes, and it has a 2 by 2 matrix for the covariance.
So it has a 2-dimensional vector for the mean, and
2 by 2 matrix for the covariance.
Okay, which has 3 free parameters.
Okay. Then we go to 5 2-dimensional points.
We go to 1 for the mean, and we have 5 2-dimensional points for the directions. Okay. Yes. Plus, for each point, you have a weight for the mean and a weight for the covariance. Right? Okay.
But so these 3, they are not the difference of the degrees of freedom of the new points.
No. These 3 parameters are imposed by you.
Yes, but why do we impose only 3 and not the difference between the degrees of freedom of the new points and the old points?
Because the directions are imposed. Now you will see why.
Okay.
Okay? But let's say now I want to give you, like, there is a way to calculate the sigma points. I'm teaching you the way on how to calculate the sigma points. In order to draw the sigma points, you have to select these three numbers, right? And these three numbers are constants that you embed in. You choose ones and then you leave them in. There are papers on how to select K based on whatever, the weather, right? There are papers that show the optimal selection of the K or blah, 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 blah. But right now we just want to have some numbers that work. Okay? Now, what we want to respond now is we want to extract from the parameters a set of sigma points. How many sigma points do we want to calculate? Well, if the Gaussian is as dimension n, we need 2n plus 1 parameters. And this is out of question. Now, the law, the holy thing says, calculate a value which you call lambda. Lambda, whatever lambda means. It's some sort of dispersion. That is calculated by alpha squared times n. It's the first parameter. Here, n is given because it's the dimension. Alpha squared is, let's say, it will count as the dispersion of the sigma points. So like the larger you select alpha, right, the further will be the sigma points from the mean. Understood? Okay? The broader they will become. Then you calculate the Cholesky decomposition, which is the square root of the covariance matrix A. A is our covariance matrix. Okay, guys? But you calculate the Cholesky decomposition of square root of n plus lambda of A. Clearly, you can also take the square root of n plus lambda, put it out, and calculate the Cholesky decomposition of A. That's completely equivalent. Okay? Clear? And then you have this matrix that we call L. Take into account that this lambda magnifies, no? Makes it larger, the matrix A. Clear? Because it multiplies it, it's a constant, it's positive, so it makes it larger. Now, if you calculate the Cholesky decomposition, then you select the sigma points, or better, the mean stays the mean. But the position of the sigma points for each dimension is you pick up the ith column of the Cholesky decomposition, and you consider this vector as positive and as negative. The time that you consider as positive, you get the first sigma point. The time that you consider it as negative, you get the second sigma point. Is that clear? So you calculate the Cholesky decomposition. This. Let's say this way. This L, right? Each of those column vectors is going to denote a sigma, the direction of a sigma point. Is that clear? Guys? That's what it means. Then clearly, the covariance matrix does not depend on the mean, right? In order to have a control point in the space, you have to take the mean and sum it to its offset, right? And then you have the true control points. So the first sigma point you will have for the, let's say, this is the order clearly, the order of the sigma points clearly doesn't matter, because in the end we are dealing with it through the sum, right? But let's say you pick up the first between 1 and n to be the positive, so you take mean plus the ith column of this Cholesky decomposition for the positive one. So you'll have mean plus the first column, first sigma point, means plus the second column, second sigma point, and so on, right? And then you have the symmetric ones, means minus the first column, mean by the second column, mean by the third column, and so on. And you get the positions of the sigma points. And the first one is the mean itself.
Why the second I goes from n plus 1 to n plus 2n?
No, it goes from n plus 1 to n. To n plus 1, or because x is with 0. This should be between 0 and n minus 1. Yeah. No, we start with 0. This is the first point is the point 0. Between 1 and n are the positive. Between n plus 1 and 2n are the negative.
We have just one point.
Mu, first point. All the points that go from 1 to n, and so we have n plus 1. And here we have from n plus 1 to 2n. From n plus 1 to 2n. I mean, normally, let's say, normally in a program, given that the order doesn't matter, what I do is that I calculate the Cholesky decomposition, and then for each column of the matrix, I calculate the plus and the minus, plus and minus, right? I get them shuffled. That makes more sense than having two different for loops for doing the same thing. But the order doesn't really matter.
So the square brackets just identify the direction.
Sorry, man. Repeat.
The square brackets just identify the direction.
Identify the column. The square bracket. What is the square bracket? These square brackets. This means the ith column of n, which is a vector, right? This means the n minus I column of L. But clearly, the game is that you have the mean, and that's the first sigma point, and then you calculate this Cholesky decomposition, and then for each column, you obtain one sigma point by taking the mean and summing it to this vector. You obtain the second sigma point by taking the mean and and summing it to the opposite of this vector. And you get plus minus. Then you should do it for the second column, for the third column, and so on. Is that clear?
Yeah, but why can we do mu minus L?
But you can use them any arbitrary order. I had to find a way to put it there. You can use it. These are the sigma points. The way you shuffle them doesn't matter. Let's say this way, because then in the end we are gonna only sum them, and so the order doesn't matter.
Yeah, but the vector Li, is it equal to the vector Ln minus I?
Yes. Yes, the point is that n goes between 0 and n, right? Well, just do the calculations, and then they are equivalent. The important thing is that you pick them up all. Okay? So what I do is that, I mean, it sucks to write it in mathematical form. If I would show you the piece of program that does it, it would be much simpler. Take a point, calculate the Cholesky decomposition, do the plus, minus, finish.
Yes, we are adding and subtracting the same quantity.
Yes, exactly.
But A is the program.
A is the covariance matrix that we want to calculate.
Oh.
They call it sigma, but I didn't want to put it sigma here because I wanted to refer to this. Right? All right. Now, we have resolved the first problem. So given the and you also understand the meaning of this parameter alpha, right? Because if alpha would be 0, right? Then we will calculate this Cholesky decomposition of 0. No, of n. Of n. But if alpha would be incredibly large, we would pick up, we would have sigma points, we would scale also the Cholesky decomposition by itself, right? But you would scale it by the square root of that thing. And so we will get sigma points, we would get vectors which are very long. So very spread. If you pick up an alpha which is rather small, then you get vectors which are closer to the thing. And the higher the dimensions, the more you have to magnify alpha in order to select these points. Is that clear? Very good. Now, the second thing is that to calculate the weights, these are the rules. No? Clearly, we have selected the vectors, but still we have the knob of the weights. If we would change the weights, we would change the shape of our distribution, because we would say, oh, this tails matters much more than the mean, and so on. So the other degree of freedom has to be selected this way. With Wm, we denote the sigma points for the mean, and with Wc, we denote the sigma points of the covariance. The sigma point of the mean, the first one, has to be selected this way. The sigma points of the covariance have to be selected this way, where alpha and beta are the parameters before, and the all other sigma points, which are the non-zero, for the covariance and for the mean are the same. Okay? Now, having said that, I would recommend you to implement in Octave, I have shown you how to make the Chol function, right? To implement in Octave a function that calculates, goes from sigma point to, from mean and covariance to sigma points, and from sigma points to mean and covariance, okay? From unscented and to unscented. It takes you probably 10 minutes to do it, only a straightforward implementation of these formulas, and then you should have it done. You can verify that it works, because if you go from mean and sigma points, from mean and covariance to sigma points and then back, then you should get this. That clear? Clear, guys? Very good. No. Okay, so what we have done is that we have introduced a new representation for the Gaussian through these sigma points. All this mechanism, all this first blah blah, was to introduce a new way of parameterizing the Gaussian. And having introduced a new way to parameterize the Gaussian, we have now to figure out how to transform its parameters under the conventional operation on distributions, which are marginalization, conditioning, chain rule, and passing through a function, and affine transform. Yeah. Okay.
Why are the sigma points found with this method better than random sigma points, for example?
Because random sigma points, the question is like, throw me, calculate random sigma points through which I will be able to reconstruct the very same mean and the very same covariance from where I started from, without approximation. You could have random, right? But how many would you need? There's a balance between the number of sigma points. So if I would have 1,000,000 of points, I agree with you. I have a Gaussian, I sample 1,000,000 of points, and I get a very nice distribution. But then we are drifting through particle filters, which we will deal with. But if I give you only 2n plus 1, it's true that I give you more parameters that will allow you, presumably, to model the manipulation, to morph the Gaussian in a more funky way. This is true, but at the same time, you lose the computation, because you will have much more points to deal with, right?
So when the points are more efficient, with less points.
With less points, you are more efficient. You gain a little bit degrees of freedom, right? You lose a little bit of computation, but that's it.
Okay.
Okay? All right. Let's go forward. So now we have a new representation, and we have to say, now let me introduce this notation here, UT. UT means an unscented transform, which means a Gaussian distribution, which is represented by a set of sigma points together with their weights. Okay, guys? Clear? Guys? And normally I refer to a sigma point, to a single sigma point with this mask cal xi, which is a data structure containing the point and the weights. Understood? Clear? Very good. Now, let's think about the first problem. I have a Gaussian distribution represented as a set of sigma points, okay? A b-dimensional distribution. This is a two-dimensional distribution for which I will have clearly 5 sigma points, okay? Each of these sigma points takes over on a space xa, xb. So let's say this is xa, this is xb. This is xa, and this is xb, right? Now, what happens if I marginalize over xp? If you remember what marginalization means that I have to take this point and project it here. 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 Right? Marginalization means collapse in one dimension. Agreed? Which is equivalent to the integral over xb of p of xa and xb. Okay? Of course, I'm deleting a dimension. Which dimension I'm deleting? I'm deleting the dimension of the variable that I'm going to marginalize. Visually, this corresponds to splattering every single point where it belongs. That's it. Of course, I will have more sigma points than needed. What does it mean, this? This basically means that I have to, each sigma point will have two coordinates, right? No? XA and XB. When I marginalize, marginalizing means removing dimensions, okay? I could simply delete from each sigma point the variable, the dimension that I'm going to marginalize. Agreed? Do you understand what I mean? I delete it, and in this way, basically, I collapse. If I delete xb, let it be xb, this be xa, I would just like collapse it here, collapse it here, collapse it here, collapse it here. And then I end up with a unidimensional distribution, which is exactly the distribution that I expect after marginalization. Clearly, I have more sigma points, yeah? But it's not an issue if I have more points. Still, I could reconstruct my distribution by calculating the two unscented as I was doing it before. With the mean, I could extract the mean and the covariance and be happy. Okay? Clear? Is that clear, guys? It's cool because you really see that it's all a closed world. Then functions. Well, functions are straightforward. What was I doing on the blackboard is exactly what you do on the unscented transform. So remember that with the unscented transform, we have the distribution, which is a set of control points, right? Now, if I have to apply a transform to this set of control points, what do? Well, I would just like apply a transform to each individual control point. So let's say that I have a function xb equals of f of xa, with xa, which is represented as a set of control points xa with I, right? And this is my function, no? 1, 2, 3, 4, 5, my control points with their weight. In order to calculate the distribution of the new points, I just like take this point over here, and which is xa with I, and I apply it to the function. And I will end up in another point, position. Right, guys? I take the second point, and I apply to the function, and then I will end up in another position. I take the third point, I apply to the function, I will end up in another position. In the end, basically, I projected my distribution of points through the function, each individual one. Okay, guys? And what do I have? I have new sigma points. What was the probability mass, the weight of what is the weight of the new point? Well, the weight of each new point is equal to the weight of the point in the source from which it generated, because by passing through a function, a point takes together all its weights. Okay? Cool, eh? So you don't need any more to write Jacobians. Do you? No. Clear, guys?
So the weights don't get transformed by this?
Your colleague says, so by applying a function, the weights do not get transformed. Exactly, the weights do not get transformed. Only the position of the points get transformed. And clearly also the domain, no? If you go to from one domain to another, also the domain will change from R2 to R1. Okay. Then let's another manipulation of the Gaussian that we were finding quite useful in our domain was the chain rule. Remember that with Kalman we restricted ourselves to have the mean of the conditional distribution, which was controlled by an affine form. In particular, the scenario is the following: we have an input distribution, which we call XA, which is controlled by a set of sigma point x's, xa with I. So we have this bunch of 2n plus 1 sigma points with their weights, right? Then we have, as output, we have another distribution, okay? This time, this distribution is a conditional Gaussian distribution. This is important. It's a conditional Gaussian distribution, okay? Which takes over the variable xb, where the variable xb is controlled by, is distributed with a mean that moves according to f of xa. Similar to what was happening in the, mamma mia, similar to what was happening in the Kalman case, okay? Okay, you remember? In Kalman we had here a mu a xa plus b, or f of xa in the unscented, in the EKF. Is that clear? Can you picture what this equation here means? I have a distribution over xb with fixed covariance sigma b given a, whose mean moves according to the input controlling parameter xa through a function f. Clear now? Very good. Under these conditions, we want to calculate P of xa and xb. Clear? And clearly, this will be a joint distribution which will have a number of dimensions equals to the dimension of xa plus the dimension of xb. So, and this joint distribution will be characterized by a mean, which we call mu of a and b, and a covariance matrix, which we will call sigma a and b. Right? Now, we very much expect that the mu a and b will be consisting of a block mu a. Mu a is the controlling mean, and so it's clearly not affected by the chain rule, because the controlling variable will have a peak, and also the peak will stay in the while calculating the joint. Okay? Similarly, mu b, the mean of the controlled variable, will be obtained by passing the input mean mu a through the function to obtain the new mean of the controlled variable. Okay? What about sigma a comma b? Clearly will be consisting of a block distribution, pretty much as it was in the plain Gaussian case, where we will distinguish the following block. Clearly, the covariance on the controlled variable sigma b of given a will be summed by the controlling block. This one here, similar to what was happening before, will stay the block of the controlling variable sigma a, which is the covariance matrix of the controlling distribution. What about these blocks over here? I don't know. Let's see what we can do. Now, let's give some intuition. I have a set of sigma points in the controlling distribution. What could I do for each of these sigma points? I have a sigma points of dimension of xa, right? I need to somehow calculate another piece of this sigma point, which is the sigma points of the components xb. xb is obtained by taking the controlling sigma point and passing it through f, right? Do you see that? And by doing this, if I consider the union xa with I and xb with I, which is the projection through f of xa with I have a larger sigma point, right? Do you see it? The union of the two. Now, consider the stack xa with I, xb with I. What is the dimension of this object? Dimension of xa plus dimension of xb. Do you see that, guys? Yes or no? I have a vector, xa. Agreed? I have a function of a vector. So your colleague doesn't see it, and now I'm sorry because they don't hear. Like, I should also, please, guys, in the lecture hall, each time you ask me a question, please remind me to repeat it for those at home, because otherwise it looks like I'm answering to the air. Your colleague requires some other, I guess at all, requires further clarification. If I take a sigma point xa, what is it? It's a sigma point of the controlling distribution. Do you agree with that? If I take this point and I pass it through F, what do I get? I get a point in the controlled distribution. No? This is the function. I get a point in the controlled distribution. Okay? I project. Now my interest, but these two entities are correlated because one is obtained by applying a function to the first. Right? What is the dimension of this point? Is the dimension of xb, right? Of the domain of the function. Agreed? What is the dimension of this object? Is the dimension of the codomain of the function, like where it was starting. Okay? So if I consider the stack xa and xb, the two, one on top of the other, their dimension will be the sum of the two dimensions. Right? And this is a perfect candidate to be a point in the joint distribution. Because the joint distribution is a distribution that takes place over the union, over the cross product of xa and xb. Agreed? Okay? Can I regard this union, xa with I and xb with I, the union of the stacking of the two, as a unique sigma point in the joint distribution of xa and xb? It's a vector that has double the components, right? Not double. That has the number of components of xa plus the number of components of xb. Do you see that, guys? Do you see that or not? Right. And I do it for one. Remember that I'm interested in getting a bunch of sigma points. Okay? So if I take every single sigma point of my input distribution and I project it through F, okay? And during this projection operation, I construct a new sigma point in the augmented space, which has in the first component the source sigma point, and in the second part, it has the leading sigma point. Do you see that? Do you see it, right? Very good. Now, don't I have a set of sigma points? Yes. New sigma points. Where are these sigma points living? They are living in the space of xa and xb. Right? Now, what would happen if you reconstruct the mean out of these sigma points? What would you expect it to happen? How do we picture them? Well, let's see. I make myself bigger. For those at home, I'd like to be able to move the screen, actually. It appears to be something not easy, because the cables have to be short, right? I want to control the cables. So my game was, I have a certain function f of x, a, and I call this xb, right? That was written in the slides, basically. Okay? Then for this xa, I have a sigma point, xa with I. Okay, guys? Now, what happens if I apply for each of those the function, and I obtain a new point, xa with I, xb with I, which is equal to f of xa with I. Okay? No. You see that? So this is this block over here. Now, this is just for clarity. Can it be a sigma point that I can call xab with I? Can't I? Yes, I can. Right? Very good. Now, let us compute the mean of these sigma points. Okay? If we compute the mean, we will obtain, what will we obtain? We will presumably obtain the mean of xa in this component, because it will be nothing else than the sum over I of W mean of I of these elements, right? So this can be split in the sum of xa with I, which is the original mean, and this will be the sum of xb with I, which is the mean of the points projected to f of xa. And we obtain the new mean, right? Now, if you calculate the covariance, we can use the outer product, which is exactly what was written in the slides. Now, to calculate the covariance out of the sigma points, remember that sigma, the total sigma, through this operation, could be recovered by the entire sigma points. What are the entire sigma points? Are these blocks over here. Now, I invite you to wrap the sums and to figure out that, let me become smaller, and to figure out that if through these sigma points that we call sigma AB, which have 10 dimensions in the dual space, you could reconstruct basically, these blocks over here. Why? What is sigma BB? Sigma BB is this component over here of the covariance matrix, isn't it? Right. Do you agree with me? Very good. How is this sigma BB obtained? Well, it's obtained by basically multiplying the blocks of the sigma point xb, the difference between xb with I and mu b with I, the difference between the point and the mean, only for this dimension over here. And that basically leads to the covariance block. So this equation here is just a wrap-up, can be directly obtained by considering this formula and applying XA and applying instead of talking about xi, you split it in xia and xib. Do you see, guys? Hello? And like the game is exercise. Take this formula over here, expand xi in xia, xib on top and on the bottom, and also mu with mu a and mu a and mu b. Okay? Execute the product, group the terms, and identify that these are the formula for sigma AA and sigma AB. It's quite easy. I leave it to you as exercise, because it really takes no more than 5 minutes. Okay? So I would pose it as, I want to do the product from this, expanding the term, so like where xi becomes xia on the top and xib on the bottom. Understood, guys? Mu becomes mu a and mu b. You write this formula over here, you do the product, and then you identify what is the top right block, the off-diagonal block, and what is the bottom block. Okay? Once you have done this calculation, you will figure out that the upper block, the off-diagonal block is this, and the bottom left block is this. Okay? I leave it to you as exercise. Please do it. It's very formative. It allows you to understand, okay, I have this bunch of sigma points, now I want to recover a joint distribution. How do I do? Well, I reconstruct the sigma without knowing anything about it, just treating them as plain sigma points. Okay? After reconstructing the sigma, you will have the blocks, you identify the blocks, and you figure out that the equations for the blocks are exactly the equations that we find here. And these equations come from the direct application of the formula that we have found in the first part.
The first block and the ball covariance matrix have the same name, but they are different things.
The first block, what do you mean?
This sigma AB, like it's the
Sigma AB, your colleagues, well, first I have to understand fully the question, and then I can repeat it for the folks at home. Repeat, please, because...
So, the ball covariance
this one over here is the entire one. This is sigma AB, right?
goes to the upper triangular block is sigma AB, but they are two different matrices.
Sigma, right, yes, they are two different matrices. The sigma, clearly that would be, you know, space temporal. They are two different things. Yes, this is the block and this is the total. Yes, this I can try to fix it on the spot for you. And how do I call it? Yes, I know how to call it. Aha. AB, BA, BB. Yeah, better? I blasted the comma for you. Just to distinguish the things. Yeah. Like, we have now a small difference in notation. Okay, guys?
Sorry, maybe it's similar to what you said before. But why do we make the relation between the old points and the new points? Right? The A points are before and the B points are new after the transaction.
Yeah.
So why do we calculate?
Because it's a controlled distribution. It's a conditional distribution. Your colleague asks, why do we make a correlation between the two? Read well. I have a conditioning distribution XA and I have conditional distribution where XB moves according to XA. XA is a fact. Right?
Okay.
So now, in order to figure out, to calculate the new sigma points, I take each fact, which is a sigma point, I pass it through F, and I get the consequence of its fact, which is the projection of XA in the XB space. It's the consequence, right? This is a conditional distribution. XA is a controlling parameter that decides how the mean moves.
Okay. But XB and F of XA are the same, right?
XB with I, one is a value, right?
Yes.
I have one sigma point, I apply this one sigma point, which is different from other sigma points, to the transformation, right, F. And I obtain its effect in the augmented space, in the codomain. I'm interested in the joint distribution, right? Joint, which means A and B. So I say, this is to this input corresponds this output.
Okay. But in the previous slide, when near the top, we say the previous.
In the previous line,
your normal of XB, F of XA. But F of XA is XB, right?
But XB is the variable, and so this means a normal distribution defined on the. Okay, your colleagues asked explanation about this thing. This is how we express a conditional distribution in a Gaussian. This means this is a normal distribution that takes place over the variable XB. Okay. The parameters of this variable are the following. The mean that is controlled by the parameter XA. If I change the parameter XA, I change the mean of the distribution. This is a family of distributions. Okay? It's not one, it's a family of, you remember that Gaussian that was sliding? I give you a parameter and you get one distribution. I change x and you get another distribution. Okay. Now, the game is that we are able to calculate the chain rule through the Unscented Transform. And once again, we had a nonlinear function and we didn't need to calculate any Jacobian. All we needed to do is to take each sigma point, calculate its extension, its addition, so to say, like which means passing to f, calculate the rest, the remaining element, and then we can reconstruct, let's say, the covariance, the joint covariance distribution, in this way. Okay? Conditioning. Conditioning is a pain, because conditioning in the Gaussian form had this fantastic equation that you basically it's a variant. You can't slice sigma points, basically. That's the big problem. So the Unscented Transform does not support conditioning by itself. So while we could marginalize in the unscented domain, so in the domain of sigma points, we could calculate the projection to a function because we were transforming each sigma point. We could apply the chain rule. Fine, cool, because we could calculate every sigma point. What we cannot do is the conditioning. Okay? How do you do conditioning in unscented domain? You go back to the normal domain, you calculate the covariance matrix, you calculate the mean, you do conditioning as you were doing the conditioning before, and then you apply the, if you want, you recover after conditioning the sigma points again. Okay? Understood? Because, I mean, doesn't come well. Remember, conditioning means slicing in the dimension of the fact. And it can't really. You have to consider all the continuum of the distribution, not just the control points for condition.
So by now we come back to the previous representation.
Yes, if you want to do all other things, you stay in the unscented domain, right? But once you need to condition, then you have to go back to the canonical parameterization. Do I manage? Yeah. No, I don't manage. I think I will have to continue. Okay. Now, I will try to introduce quickly the unscented, the game of a nonlinear system. As always, so we are in the filtering domain. We have a system with Gaussian noise. I think I've been quite verbose on that. This is our transition function. This is our observation function. We have additive zero mean noise, which is added to the controls, and we have additive zero mean noise, which is added to the observations. Our assumption is that we relax the assumptions here, right? We relax the assumption because we say that this function here is not anymore linear. This is a generic nonlinear function, and also this one is a generic nonlinear function. Normally in Kalman, we were assuming to have a system which was an affine form, AX plus BU, and so on. Okay? Now we are kind of relaxing it a little bit. Now, we would like to use what we have learned, the manipulations that we have learned on the Unscented Transform to construct a filtering machinery. Okay? So, what we have learned is how to marginalize, how to pass through function, how to apply the chain rule, and how to apply the condition. Right? Okay? Which means, if we remember our proof of the Kalman filter, we have everything in place to basically maintain the very same formal implant, which is doing the very same operations, only that we will do them with a different representation, which is the unscented representation. Okay, guys? Agreed? Very good. The good thing is that we didn't have to calculate any Jacobian in the game, because we didn't have to do any linearization. Additionally, by having more control points and doing this operation of projection and unprojection, we might expect that the Unscented Transform better models the effects on the tail of the distribution, and this is typically verified and demonstrated in many papers. Okay? So, if you can, using the unscented transform is not a bad idea. Also because it's not more complicated than the traditional Kalman technique. Okay? Now, how would you implement predict? Remember the machinery, this is a proof of the proof of Kalman. Remember what was the filter you all know that evolves in the predict and in update step. In the predict step, we have as input the previous state distribution, we have the control together with its noise, and we would like to calculate the next state distribution. In order to do so, what we can do and what we used to do is to know that we have an initial distribution which is represented of the joint between the state and the controls, which is represented by a mean, mu t minus 1, t minus 1, and a other piece of mean, the mean of the control, mu u at time t minus 1, and we also say that this, the controls and the mean are uncorrelated. The controls have covariance sigma u t minus 1, and the state has a covariance sigma t minus 1 given t minus 1, right? This is the input of the prediction step. The output will be straightforward, will be, we would like to have the output as an unscented transform of this. So what do you do? What is reasonable to do? You have this fantastic, spectacular joint distribution expressed in a momentum form. What is natural to do to apply what you have just learned on the unscented transform? We would like to extract a set of sigma points from this distribution over here, and to take each of these sigma points. Remember, each of these sigma points takes place in the joint space x and u. Okay, because it's a joint distribution over x and u. Okay, guys? Do you see it? Now, this is a function of two variables. The input of this function is two numbers, right? So, if I have to consider the joint distribution over these two numbers, each element of this joint distribution will have a little piece of x and a little piece of u. Okay? Very good. So what is natural to do? Well, very first thing, now we are strong with the unscented transform, we have the way on it, how to extract the sigma points. So I take this joint distribution and I extract a bunch of sigma points, which I call xi t minus 1, t minus 1, right? Remember that each of these sigma points lives in the space of x and u. Okay, guys? Understood? It's a joint. No? It's not the thing that you smoke. It's joint distribution, united distribution. Okay, guys? Clear? I have this bunch of sigma points. Remember that they live in a dimension of x plus dimension of u. Clear? And then it's super easy, because then we can just say, take each of these sigma points and project them through the transition function. Remember that each of these sigma points contains a little bit of the x part and a little bit of the u part, right? Clear? Hello? Yes? No? Maybe? Yes. Very good. So each of them, and so we get a bunch of sigma points in the target distribution, which is the target distribution. What is it? Is the next state distribution. Basta. We have done the predict because we have a set of sigma points. And these sigma points will be distributed according to xt given t minus 1. So the distribution after the prediction. Okay? We do one step forward through the transition function. Okay?
So the nonlinear function is the transition function.
Is the transition function? Is this f? Okay. Only that each of those clearly will contain a piece of x and a piece of u.
Like before was a piece of xa and xb.
No, that's another story. Don't mix it. We will go back to that. Okay. No? Now we are just composing the things. Right? Understood, guys? Let's go on. Now, update. For the update, remember what we had to do. We have the probability distribution of xt given t minus 1 which is in this case expressed as an unscented, in unscented form, so a set of sigma points. And we have the conditional distribution of the measurements given the state, which we can see as a distribution over z of t whose mean is controlled by h, which is my observation function. Agree? Very good. We have seen it before. Now, in order to calculate the joint distribution, we could use the trick of the chain rule that we have seen one slide ago. So, how do we do? Well, simply, we take each sigma point in the prior distribution, xi t given t minus 1, which is the sigma points that we obtained by the predict step, and we calculate its counterpart in the measurement space. We call it zi with t. Okay? Clear? We can calculate the mean straightforwardly in this way. No? The mean of the observation will be just like the mean of the projected sigma points. That makes sense. And then we can calculate the cross correlations exactly as in 2 slides ago. So we can calculate the sigma x given z, which is a matrix which is as tall as x and as wide as z, by taking by calculating the sum of the outer products between the difference between the state mean, the sigma point, and the state mean, and the difference between the corresponding sigma point in the measurement and the measurement. And you will get something which is consistent with the off-diagonal block of the covariance of the joint covariance matrix between states and measurements. And then you can do the same. So this is a straightforward application of this rule over here. Just change the letters, and you will find that it's exactly the same. Do you see it? It's just one-to-one. Before we have seen a rule, now we are applying the rule. Interesting, right? We calculated the joint distribution over the whole. Then, well, and then at the end, what was the final step of the prediction? We have a joint of the update. We had the joint distribution over state and measurements, and then we need to actually condition on the actual measurement. Conditionally, unfortunately, cannot be done in unscented form. So we take this funky matrix, funky matrix that we obtained before, which actually we obtained it already in a closed form, and we apply conditioning exactly as we were doing in the Kalman filter case. And then we have led to the unscented Kalman filter. That was it. Nothing else. And then we have this fantastic slide. I mean, I'm really proud of it because I invested time to give you in one slide all the concept of the unscented Kalman filter. Everything starts with the prediction step, where you have the joint distribution over previous state and controls, which is expressed according to this covariance, mean and covariance. Then you calculate the sigma points, you apply the transition, and you get the sigma points in the next state space. Then, in order to apply the update, then you have to project each of these sigma points in the measurement space through the function h, and then you have also to calculate the mean of the observations, just like by calculating the mean of the projected measurements, sigma points of the measurements. And you end up here. And the final step is that you can calculate the components of the joint distribution in the following way. Okay? Which is the application of the chain rule to the unscented transform. Once you have the joint distribution over predicted state and measurement, then you can apply the update, which is the conditioning, exactly in a Kalman way. So you basically condition on the actual measurement that you have got. And that concludes. If you are interested in more things, here are some references, and please have fun. My suggestions, I think tomorrow we're going to see the UKF in action through a simplistic localization thing. It's tomorrow that we have lesson, right? I don't know. I have lesson every day. I don't know when. tomorrow here, right? That tomorrow we will be on the stage and we will have fun, I guess. And I'm proudly streaming on the phone, through the phone, and we didn't have any network issue. So, bye-bye.